In this session, I will be discussing about the stresses in bars of varying cross sections. Varying cross sections. So, in the previous session, I think we have discussed about the stresses in uniform bars, in bars of uniform sections. Okay. Now, when bars of different sections are connected together and subjected to axial forces, what will be the stresses in each of these bars and what will be the elongation of each bar and total elongation. So these forces may be tensile or compressive. Okay. So let us consider first a bar, composite bar made up of three bars of different sections having areas A1, A2, A3 and lengths L1, L2 and L3, and it is shown in the figure. Okay, and subjected to an axial tensile force P. Okay, now what will be the total elongation of this? How to find the total elongation and what will be the stress in each of this component of this bar. It has three portions: AB, BC and CD. AB with area A1, length L1, BC with area A2, length L2, and CD with area A3 and length L3. Okay. Yeah. Let us see. To find the total change in length, which will be equal to the sum of the changes of all individual lengths. Okay. Now, as we have discussed, P is the axial force acting on the member. E is Young's modulus of the material. We will assume all the three sections are of same material. So, Young's modulus is same for all the three sections. It is possible that two different metals may be connected together and subjected to axial force. In such case, the Young's moduli will be different. Okay. So for section 1, the area A1, length L1, A2, L2, A3, L3 are corresponding values for sections 2 and 3 as shown in the figure. So now, each of these segments is subjected to the same tensile force P. That means if you consider the free body diagrams of AB, BC and CD, for equilibrium, if you consider the equilibrium of this, the resisting force acting at B will be P only. Okay. Similarly, if you consider the segment CD, the resisting force acting at C will be P again, acting to the left. So at C in portion BC, you will have force P to the right, towards right, and at B you will have force P towards left, so that these two are balanced. Similarly, these two are balanced. We are considering the free body diagram. We are considering each portion separately by cutting the member at B and C. Okay, the free body diagrams will obtain. So now the portion AB is under tension. A tensile load of P is acting on it. So the extension of the member AB, portion AB, will be delta L1. Let delta L1 be the extension of portion AB. And delta L2 is the extension of portion BC, and delta L3 is the extension of portion CD. So the total extension of the member is the sum of the individual extensions of the portions AB, BC and CD. It is clear. So we have to find delta L1, delta L2, delta L3 and so on, and add them to get the total elongation or compression. If the force is compressive force, compressive in nature, then we will have the decrease in length actually. Okay, either decrease in length or increase in length, it doesn't matter. So the total change in length is equal to sum of the changes in length of different portions. Okay, so delta L1, which is equal to PL by AE actually. So here length is L1, area is A1, and E is same for all the three sections. So PL1 by A1E. If material is different for different portions, then we may have to write E1, E2 and so on. Okay. Here we are considering same material for all the portions. So E is same for all the three sections. Okay. So PL1 by A1E. Next for delta L2, extension of portion BC, PL2 by A2E, and delta L3 is PL3 by A3E. If there are some more lengths, then we have to add it up. Okay, this clear. So here by summing up, you will get the expression as P by E is common here into L1 by A1 plus L2 by A2 plus L3 by A3. This is the total extension of the member consisting of different portions with different cross sections and lengths. Okay. If it is a member of uniform section throughout, then we will have A1 equal to A2 equal to A3, and this becomes P into L1 plus L2 plus L3 by A. If the member is of same cross-sectional area, uniform section throughout, then this formula reduces to this, and it is PL by AE actually, where L is L1 plus L2 plus L3. That already have seen for uniform sections. Okay. Now, the modulus of elasticity is different sometimes. In that case, the equation is it takes this form. Okay, P into L1 by A1 E1 plus L2 by A2 E2 and so on. Okay. Yeah. So this is how we'll find the total elongation of the member consisting of different portions of different areas and lengths. And coming to the stresses in members, uh, sigma 1 in the previous case. Here, sigma 1, the stress in portion AB is P by A1. Okay, similarly, sigma 2 is P by A2. Okay, so on. Is this clear? Yeah. Next, let us consider some numerical examples. Remember, ABCD is subjected to two point loads P1, P2, P3, and P4 as shown in the figure. Calculate the force P2 necessary for equilibrium if P1 equal to 4500 newtons, P3 equal to 45,000 newtons, P4 equal to 13,000 newtons. So determine the total elongation of the member assuming the modulus of elasticity E equal to 2.1 into 10 power 5 Newton per mm square. So this is a different case actually. What we have discussed is the total member is subjected to the same tensile force P in the previous example what we have discussed. Okay, but here different forces are acting at different axial forces only at different points along the beam. We have different forces acting towards left and towards right. Okay, but the thing is these forces must satisfy the condition of equilibrium. Okay, so P1 is given which is acting towards left and other forces acting towards left here are P3. So P1 plus P3 must be equal to P2 plus P4. The forces acting towards right. So to satisfy this condition, what is P2? That you need to find out. So P2 is P1 plus P3 minus P4. That is 4500 plus 45,000 minus 13,000. So it is 36,500 newtons. Okay. So first you have to find out the force P2 which satisfies the equilibrium condition. Okay. Now we have to find the total elongation of the member considering each segment separately. So consider AB, BC and CD, the free body diagrams of these three portions, and find the elongation of each of these segment. Okay, it is clear. Okay, so the force P2 is 36500 newtons. Okay, now the free body diagrams of this each segment here, areas are given, lengths are given. Okay, areas of the portions AB 6.25 centimeter square, BC 25 centimeter square, CD 12.5 centimeter square. And lengths are 120 centimeters, 60 centimeters, and 90 centimeters, respect. Now, considering AB, each of this segment must be in equilibrium because the total body is in equilibrium. Total composite member is in equilibrium. So each of this segment must be in equilibrium. Okay. So at A we have a force of 4500 newtons to the left. So towards right at point B, you should have an equal force and opposite in direction to 4500. It is clear. So you must have a force of 45,000 newton, 4500 newtons at B. But actually, what is the force acting at B P2. Of this is 36,500 P2. So of this, member AB takes a force of 45,000 and remaining 32,000 we have, that will be acting at B towards right. Okay, so that the sum of these two is P2, 36,500. So now on portion BC, you have a force of 32,000 at B acting to the right. So for equilibrium of this, you must have a force of 32,000 newtons at C also acting to the left. Next, at C, for portion CD, at C, what should be the force? The total force at C is 45,000, that is given, of which 32,000 is acting at C for BC. Remaining 13,000 will be taken by CD. Okay, will be acting on CD. So the member CD is subjected to a tensile force of 13,000 newtons. Okay. Now the extension of portion AB is P1 L1 by A1E. Here P1 is 4500 newtons, L1 is 120 centimeters, A1 is 6.25 centimeters square, and E is 2.5 into 10 power 2.1 into 10 power 5 Newton per meter square. So before substituting these values, you have to convert them into same units actually. Okay. So here L is in centimeters, A also is in centimeter square units. So you first convert them into mm and mm square. Okay. Same is the case with delta L2, which is P2 L2 by A2E, and delta L3 is P3 L3 by A3E. Okay. So substituting the values, we can calculate the extensions delta L1, L2 and delta L3, and by adding this, by actually if you see, so algebraic sum we have to find. Okay, member AB is subjected to tension actually, so delta L1 will be increasing positive. Okay, that means there will be an increase in the length of AB. Similarly, portion CD is also subjected to tension, so delta L3 is also positive because it is the increase in length of CD. Coming to BC, it is subjected to compression, so delta L2 is negative, that is the decrease in length. Okay, there is a decrease in length of portion BC. So when you sum up, delta L is equal to delta L1 minus delta L2 plus delta L. This is to be taken with negative sign as it is a decrease in length. Okay. So by substituting the values, you will get delta L1 0.041 mm, delta L2 0.037 minus sign because it is decrease in length, and delta L3 0.045 millimeters. So the total change in length. Next, So this is first example. Let us see another example. A steel tie rod of 50 mm diameter and 2.5 meters long is subjected to a pull of 100 kilonewtons. To what length the rod should be bored centrally so that the total extension will increase by 15% under the same pull. The bore being 25 mm in diameter. Take Young's modulus 200 giganewton per meter square. So I hope the problem is clear. So the bore of length 2.5 meters and 50 mm dia is subjected to an axial pull of 100 kilonewtons. Okay, and under this it will elongate. It will be elongated. Okay, by delta LC. Okay, so now if you increase the load, elongation also increases. Okay, but without increasing the load, the extension, the total extension is to be increased by 15%. Okay, under the same pull. So what you have to do? The bar is of diameter 50 mm. Okay, so we cannot change the diameter of bar. Instead, we can cut a hole. Okay, we can cut a hole so that the cross sectional area in this portion of length x will be decreased. The diameter of borehole is 25 mm. Okay, so when area is decreased using the relation PL by AE, the elongation of this portion will increase under the same pull. Okay, the elongation of the portion in which the bore is cut, the borehole is made, will increase because the area is decreased because of the borehole. I hope it is clear. Okay, so to have an increase of 15% in the total extension, what should be the length of borehole? That you need to find out. Okay, that is if delta L is the initial extension without borehole and delta L dash is the final extension with borehole. So what condition it should satisfy? Delta L dash minus delta L by delta L into 100 is equal to 15. Okay, so the percentage change in extension is 15%. Okay, yeah. For that, what should be the length of borehole? That you have to calculate. Okay, the borehole is of diameter 25. So this is the data given in the problem. Okay, so area of solid rod pi d square by 4, that is 50 mm dia. So it is 1964.3 square millimeters. And area of reduced section by after cutting hole in that portion, the area of cross section will be A2, we are denoting it, which is equal to what will be the area. So we are cutting a central hole of 25 mm and total dia is 50. So area of this shaded portion is pi by 4 into capital D square minus small d square. Okay. Capital D means outer diameter. Small d means diameter of hole. Okay. And it is coming out to be 1473.2 mm square. So elongation of solid rod without borehole is PL by A1E. That is clear. Okay. So it is coming out to be after substitution 0.636 millimeters. Okay. And elongation of bore rod after a bore is being cut, what should be the elongation? It is 15% more than the solid rod. That means the elongation of bore rod delta L dash is 1.15 times 0.636. Okay, 15% more. 15% more. That is 0.732 mm. Now, if x is the length of bored portion, L minus x will be the length of solid portion. Okay. So here we consider two sections separately now with length L minus x, the solid rod, and with length x, the bored portion. Okay. So two different segments we will consider because this is of area A1, this is of area A2. Same as in the previous case. Okay. What will be the total extension? If you call it delta L1, if you call this delta L2, then the total extension is delta L1 plus delta L2, isn't it? Delta L1 will be for this length. P L1 means this length, L minus x. P into L minus x by A1E. Next, for this portion, the force is same, P. Okay? P into x by A2E. It is clear? And this is equal to delta L dash, total extension. Total extension, uh, this is total extension delta L dash, okay, which is 1.15 times delta L. We have calculated this as 0.732 millimeters. Okay, so that is delta L dash here, which is given as delta L1 plus delta L2. Okay, understand? So delta L1 for a length yeah, by substituting this P into actually P into L minus x, P is 100 by A1 is 1964.3 into E, 2 into 10 power 5. Okay. This load also is to be converted into newtons, 100 kilonewtons. So 100 into 10 newtons. This is delta L1 plus delta L2, which is 100 into 10 cube load into x by A2 is area of reduced section. Area of reduced section is 1473.2. 1473.2 into E, 2 into 10 power 5. So this is equal to 0.732 millimeters. So by solving this, we will get X value. Okay. So which comes out to be 1124 mm. 1124 mm. Okay. It is clear. So the length of borehole should be 1.124 meters out of 2.5 meters length of solid rod. We have to cut a borehole up to a length of 1.124 millimeters. Okay, so that the total extension is 25% more than that of the solid rod. Okay, yeah, this is a second example. And third example, if you consider a steel rod of 20 mm dia and 800 mm long is rigidly attached to an aluminum rod 40 mm dia and 1000 mm long, as shown in the figure. The combination is subjected to a tensile load of 40 kilonewtons. Find the stress in the materials and the total elongation of the bar. Young's modulus for steel 200 gigapascals. Young's modulus for aluminium 70 gigapascals. So these are all similar problems. Only thing is, as we have discussed, if Young's moduli, different materials are used, then Young's moduli also will be different. Okay, so delta L is delta L1, that is P into L1 by A1E, L2 by A2. That's all. Okay, in the E1 and E2, because the materials are different, Young's moduli will be different. So here substituting the values of P, which is 40 kilonewtons. Okay, load is 40 kilonewtons. L1 800 mm, L2 1000 mm, and A1 is pi by 4 into 20 square, and A2 is pi by 4 into 40 square. Okay, and Young's moduli are given 270. 200 into gigapascals, that is 10 power 9 pascals. It comes out to be 2 into 10 power 5 only. 2 into 10 power 5 megapascals. Okay, 2 into 10 power 5 megapascals, and EA is 7 into 10 power 4 megapascals. That is Newton per mm square. Megapascal is Newton per mm square. Okay, yeah, that's all. So extension of portion 1 AB is delta L1, and that of portion BC is delta L. Everything is known, just by substitution you will get. Okay. Similarly, stresses. Stresses are P by A. Here load is same in both. Load is same in both the segments. So PS by AS, that is 40,000 newtons by area 314.3 mm square. Similarly, sigma AL is 40,000 by area of aluminium bar. So total extension P1 L1 by A1 E1 plus P2 L2 by A2. Okay, just by substitution you will get delta L1 0.37 and delta L2 No, plus. It's not minus, plus. Okay. So the total extension will be the sum of these two. Okay. Yeah. That's all for today's session. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.